Thank you. All right, we're just going to set things up here for a second. Good. All right. Everyone hear me just fine? Make sure I sort of get my where I'm supposed to be here. So tonight I'm going to be talking to you about the universe as best as I can tell you from beginning to end. Now, I'm obviously going to take some shortcuts tonight because there's a lot to talk about in the universe. First thing I want to remind us is about this being the International Year of Astronomy, which is, as was already said, was the year that Galileo first, we often say, invented the telescope, which isn't true. Galileo did not invent the telescope. He was just, in fact, the first person who knew how to use one. And so he used the telescope to look up the heavens where they were meant to be used. They're actually used as a military device that was classified by the British before that. But Galileo peered at the heavens with it, and this had a fundamental significance to science and astronomy because it changed our view of the world. Before Galileo, Copernicus came up with a theory most of us are aware of, that the Earth is not the center of the universe, something that goes back to the Greeks and even times before, and was indoctrined in the religion and society of the day. Now, what you may not realize is that although Copernicus came up with this idea and published about 50 books that had it in it, he was largely ignored by everyone, as it was just a theoretical idea where things went not around the Earth, they went around the sun. And in terms of practical everyday life of trying to predict where the planets are and things, it didn't do any better than the Greeks' very elaborate system of epicycles, of things moving in circles more or less around the Earth. But it was Galileo who went through, used his telescope and looked at a planet such as Jupiter. And this is more or less what Jupiter would have looked like to Galileo, a smudgy orb, not a point like a star, but something was bigger than that, with 4 moons that went not around the Earth, but around Jupiter. Suddenly it was very clear that the Earth was not the center of this system. He looked at the moon, he saw mountains, he realized it looked a lot like the Earth. The idea that Copernicus had, that the Earth was not particularly special, suddenly you could see it with your own eyes. And one thing I learned as being an observational astronomer, dealing with my theorist friends, is that seeing is believing. A theory is only as good as what it predicts and what you can see and test it. And so that's what my life is about, is going out and testing the universe that we live in and trying to come up with a theory that predicts what we see. So before I go into the detail of trying to explain my introduction of what is this stuff that we have discovered and giving a tour of how the universe sort of works, I thought maybe we would take a quick tour of the universe. And this universe is to get us, this tour is to get us all on the same page. Because I know what all these little things are in the universe and how the universe is, you know, I have the map of the universe more or less in my head because I'm always staring at it, but I know many of you don't. Now, to understand the universe, we need to use a ruler which is a little different than you're used to using. And we use the speed of light. And the reason we use the speed of light is because the scale of space is so huge that it's really the measure that we can sort of get an idea of, because we can turn the speed of light and time into a distance. So light travels 300,000 kilometers per second in 1 second. 300,000 kilometers per second. And so in 1 second, it'll go around the Earth 7.5 times. So that is a distance we can understand. It obviously travels very quickly, but it doesn't travel infinitely fast. So let's look at the universe around us in this ruler. So the Earth, Moon, 1.5 light seconds apart. So when Neil Armstrong in 1969, which is conveniently 40 years ago, hopped on the moon and said his memorable quote, we actually heard him 1.5 seconds after he said it, because that's how long it took the light to get to us. Now, most of us probably don't have a good feel for how big the sun is. The sun is really quite enormous relative to the Earth. It's 5 light seconds across, so it's much bigger than the Earth-Moon system itself. Most of us know, I was certainly taught in school, that we are 8 light minutes, the Earth, from the sun, but we may not have a better idea of how big the solar system is. Our solar system extends out to about 10 light hours, which to something I would call the planet Pluto. Now, it turns out that my comrades in astronomy did not share my view that Pluto was really a planet. They now call it a dwarf planet. Now, that was a fairly controversial decision made a few years ago, but I'm afraid that I personally see that a planet, once a planet, always a planet, and so I was kind of, well, slightly distressed that Pluto lost its name of a planet, but just because something else happened to be found similar to it. So Pluto is still a member of our solar system, but it is certainly not the only thing like it out there. And so now we have 8 planets, but the planets sort of go out to about 10 light hours. So let's move even further afield to the nearest star. Now this is a star, Alpha Centauri, which, if you come and sit on my back porch, you can see this star. But in Canada, you're going to have to be able to look through the ground because Alpha Centauri never rises above the horizon. It's really a southern star. And it's 4.3 light years in distance. Now, that's a lot further than the 10 hours I have just told you. So let's just put this in perspective. Alpha Centauri turns out to be a very near sibling to our sun of a star. It's just slightly larger, but only a few percent. So Alpha Centauri, if it had the scale of being, for example, a P, and our sun were another P, and if you ask yourself, well, how far apart would they be? Well, the answer is, if we're here holding the sun as a P, then Alpha Centauri would be roughly located at Ottawa in distance. With everything between us, space, empty space, or very nearly empty space. And what's quite remarkable about that vastness of space is we're in one of the most interesting places in the universe, a galaxy. Our galaxy, the Milky Way, about 30,000 light years across, well, sorry, we're about 30,000 light years from the center, it's slightly larger across, looks something like this. Now, amazingly enough, the picture I have up here is not the Milky Way. It's a galaxy that looks a lot like the Milky Way that has, and astronomers love romantic names, NGC 891 is the name of this galaxy. And you can see it sort of looks like a fried egg. And if we looked at it from, instead of the side, we looked at the top, it would look something like this, where we have the sun, our solar system, out near a spiral arm 30,000 light years from the center. Now, our galaxy has some nearby friends. These are what we call local galaxies. So these local galaxies extend out to 2 million light years in distance. So the Andromeda and Triangulum spirals are visible in the autumn here in Canada. I have to look through the ground in Australia to see those. So those are something you can more easily see than we can. The Milky Way has 2 interesting little galaxies, which when you come to Australia and visit, you can see the large and small Magellanic Clouds, which really do look like puffy little clouds. They're quite easy to see if you're in a dark place, and they're satellites of our Milky Way, and they're 185 to 200,000 light years in distance. Now, this is just the nearest part of the universe, and I want to emphasize that each one of these galaxies I've shown you here has roughly 100 billion stars like our sun. Some smaller, some larger. Our sun's relatively typical, a little bigger than average actually. So, but there is a lot of stuff out there, especially when we look further afield. And this is a map of the nearby part of the universe, sort of the suburb around our own Milky Way, extending out to 1 billion light years. And this map was made in Australia, where they went out and looked and did this census, and I'll talk about this again later of why this is interesting. They did this census of galaxies in the nearby universe, and there's 250,000 little dots in this picture. And you can see that the galaxies form this sort of cosmic foam, or we like calling it a cosmic web of structure populating the universe. But as I said, this is the suburb. If we look further and further afield with larger and larger telescopes, or as politicians like to describe them, more and more expensive telescopes, astronomers are always asking for the next bigger model. So our best model right now is still the Hubble Space Telescope, which fortunately was repaired and should be working brilliantly in the very near future. And so if we take the deepest picture we can, so by looking further and further away, of course, we're looking back into the universe's past, because light takes time to reach us. So this is the most distant picture we have of the universe, and we're looking back roughly 12 billion years into the past. So there's one bright star, which, because I'm tied to the microphone tonight, you can see the big bright thing that's got a little cross around it. That's actually a star in our own Milky Way. Everything else in that image is a galaxy. And the faintest little dots there are the objects that are 12 billion light years in distance. So astronomers like to build bigger and bigger and more expensive telescopes. We have soon the James Webb Space Telescope, which your foresighted government has actually made Canada part of. My government has not been quite so foresighted. But that telescope will be able to look even further, but only to about 13 billion years in the past. So why are we spending all this extra money to go back only an extra billion years? And the reason is that we can really only look back about this far, 14 billion years, because we run out of universe. And we don't run out of universe in distance, we run out of universe in time. This is a picture of the universe 14 billion years ago, when the universe was roughly 380,000 years old. And what we're seeing here is not a universe of galaxies, we're seeing it as a universe full of gas. And so the little bumps, you can see these little splotches on this image. The average splotch in here really represents about 10,000 to 100,000 galaxies worth of material. And the whole universe at this time is glowing like the sun. It's about 3,000 degrees centigrade, so it's a little cooler than the sun. But you can no longer see through it. It's not transparent like the air in this room. It's like trying to look through a glowing neon sign that happens to be millions of light years thick. So at this time, we can't see back any further. This image is not taken with an optical telescope. It's taken with a microwave telescope in space. And that probe provides us this earliest view of the universe. Before that, well, we sort of run into the beginning of everything, the Big Bang. All right, so that's our quick tour of the universe. We're all oriented, okay? Now let's go through and try to understand how we sort of understand the scales that I've talked about and how the universe is constructed. So I'm going to take you back to the beginnings of cosmology. And the beginnings of cosmology starts from probably a place that most of you are unaware of. This man, Vesto Melvin Slipher, is one of the heroes of cosmology, partially because his family actually had a scholarship, which I got at the University of Arizona. And I have to admit, when I got it, I didn't know who Vesto Slipher was. And then the fact that it ended up being one of my heroes, I find quite remarkable, although I'm kind of embarrassed. So I'm spreading the great word about Vesto Slipher. Vesto was really employed to look at Mars with the Lowell telescope. So Percival Lowell was a philanthropist who was really interested in Mars, and he wanted Vesto Melvin Slipher to go out and map the canals of Mars. So Vesto did that, but he also did other things on his side because he was really a scientist. And one of the things he did is he took the light of galaxies, spread them out using a prism, or we sometimes use gratings, but they spread out light into the colors, which we call a spectrum. And when you spread light of a star, for example, into the spectrum, you see the colors of the rainbow, but you also see places where a star like the sun seems to not emit any light at all, or very little light. And those little things, which we call spectral lines, are the fingerprints of elements. So for example, sodium here, and you can see on the diagram, there's a little place, there's two little dark spots, which are two colors, which are sort of a yellow-orange color, that if you ever drive around an airport at night, you will see there are often these yellowish-orange lights, which are amazingly enough sodium lights. And sodium lights emit light in this orangey color. Turns out if you have sodium in the sun, it absorbs the light, but it's the same fingerprint, just in a plus and a minus sense. Now, we also have the sun is full of iron, scandium. Helium was actually discovered in the sun, that's why we call it helium, before it was discovered on Earth. They could see the fingerprint of it, but they didn't know what it was. And so it's a very powerful technique. So when Slipher looked at galaxies, he realized they looked an awful lot like the sun, but there was one difference. The light was stretched to the red. And so if you take light, now light, as you recall, is a wave. And we talk about waves. you characterize a wave by how far it is between the peaks and the troughs of the wave. So you have the wave going up and down. If those waves are very close together, that's blue light. If they're further apart, it's red light. And so if I'm running towards you, emitting light, the light is, those troughs and peaks are going to be compressed, making the light a little blue. Now, you may think that this is why BMWs, when they come to you, have blue lights and your Toyota Corollas don't. You've got to be moving very close to the speed of light for this to be an effect. So it really is an astronomical effect. Of course, if you're moving away from something, then those troughs get spread out and the light is shifted to the red. So Slipher saw that every single galaxy, minus one or two, were all stretched to the red, and so he realized that the universe had this funny thing, the things in the universe were moving away from us. And he didn't understand this. So this is a cosmic conundrum in 1916. Why were all the galaxies in the universe moving away from us? It would seem that we were a special place in the universe. So since the time of Copernicus, which you already talked about, we thought we weren't a special place. Why would we be in a special place in the universe? Here, it seemed like we were a very unpopular place in the universe. Everything is moving away from us at quite remarkable speeds. So that problem remained with astronomy until work went through in measuring distances. So astronomers are really bad at measuring distances. We have no rulers in space. So we have to do things by any way we can get around. And one of the ways that we use is we take for example, we take a physical law that Newton figured out, that if you have a light bulb, let's say a 100-watt light bulb, and I have a detector that counts how much light there is, for example, a photovoltaic cell that you might use to generate solar energy would do this. If I take that light bulb and I move it to half the distance, then the light bulb is going to appear 4 times brighter. We call that the inverse square law, or essentially an object becomes fainter by the square of the distance. So that means that if we have a bunch of 100-watt light bulbs spread out in space, and we see how bright they are, we can measure the distances to those 100-watt light bulbs. Well, we don't have 100-watt light bulbs in space, but this doesn't stop astronomers. So in 1929, Edwin Hubble, who had access to the biggest telescopes on planet Earth at the time, the 100-inch Hooker telescope that was just outside of Los Angeles, went out and he used the brightest thing, the only thing he could see in these galaxies, which were the brightest stars. And so what he found, and he assumed that the brightest stars in all the galaxies were exactly the same brightness. Now he knew they weren't exactly the same brightness. It turns out that if you go to one galaxy and compare it to the brightness of the brightest star in another galaxy, typically to about a factor of 10, they're the same. Now, a factor of 10 doesn't sound very good, but for astronomers, that's not bad. We're happy with factors of 10. We're just looking for anything to give us a clue of what's going on. And so he did this test, and what he found out was that the more that the galaxy's light had been stretched, the fainter the stars in that galaxy were. And he came out and he said in 1929 with that measurement, the universe is expanding. Now, it may not be exactly obvious to you why he said that. We'll get to that in a second. I always like to show Hubble's data from that 1929 experiment, because I'm going to show you my own data later on. And so Hubble's data here shows distance along the bottom and how fast the object is moving away on going up. And so you can see that as you move to the right of this diagram, that the velocities on average go up. And he drew a line through it, and he said the further away something is, the faster it's moving. And Hubble's data was not beautiful, but it was enough for him to make a conclusion that turned out was only off by about a factor of 10, but he got the sign right, so we give him credit for it, which is that the universe was expanding based on this. So why do we think the universe is expanding? So here is a toy model of the universe, which thanks to the wonders of PowerPoint, I can expand by 5%. I can also make it smaller, make it bigger. You can really play God sometimes with the universe with PowerPoint. So what I'm going to do is I'm going to overlay, to make this easier for you to see, my images at one spot. So if you look at that little point where the green or gray arrow is, and look at the points nearby it, when I've expanded the universe, those points have all nearby moved away a little bit. but the points on the far part of my toy picture have moved away a lot. So this diagram, if I expand the universe and you think of velocity as being how much distance you travel in an amount of time, so as I'm expanding my universe here, the velocities of these distant objects are going to be large. The ones nearby are going to be small. I'm going to see exactly what Hubble saw. The further away, the faster the object moves. Furthermore, if I overlay this in a different spot, so it's the same picture, I haven't changed anything, I've just changed the overlay, I see exactly the same thing. So in an expanding universe, everyone sees the same thing. The further away an object is, the faster it's moving away. And so that is why Hubble said the universe is expanding. Now, it turns out that Hubble said that he knew nothing of any of the theory of the time, which is almost certainly not true. But there was a theory that actually predicted that the universe should be expanding, although the person who did the theory didn't quite realize. I mean, he actually realized it did it, but he tweaked it. And that theory was Einstein's theory of general relativity, or his theory of gravity. It doesn't get as much press necessarily as Einstein's other theories, but it's actually, I think, to most physicists, his most important contribution of many important contributions. So Einstein's theory of gravity predicted that there was a fourth dimension which was involved with gravity, and so that space would be warped under the presence of gravity in a fourth dimension that is partially related to time. And he predicted that, for example, around the sun, that light would be bent and have to travel in this fourth dimension and go in a slightly crooked pattern relative to what you would expect in 3 dimensions. And so it was a very elegant theory, but again, it was a theory. So people went out. Turns out that a theorist, and theorists should never be allowed to do observations. That's a thing I've learned. Arthur Eddington was convinced that Einstein might be right, and so he set up, right after World War I, an expedition to go out and see the effect where an eclipse happened. So a solar eclipse happened, and you take a picture of the stellar field, so the field of stars, and then in the eclipse you take a picture as well, because it's actually the sky's dark enough you can actually see the stars again. And then when you can compare those two images, you can see if the stars are stretched in a different place because their light has been bent by the sun. So it turns out that Eddington, who was a Brit, got the Astronomer Royal to go out and do this, and then he went and did another expedition at the same time on the other side of the Atlantic. So they're on 2 sides of the Atlantic. Unfortunately, the Astronomer Royal got clouded out. So Eddington had his own observations. But Eddington showed the world in 1919 that Einstein's theory of gravity was correct. I think when we look at the data now, we realize that there was no way Eddington's data was anywhere near good enough to actually do that. But that is the thing that made Einstein famous, was those observations. From my Australian point of view, the real observations were done in 1922 in Australia. Not by Australians, but by people from California who came out and made the real observation. But nonetheless, it comes down to, you can have a great theory, but until you actually use a telescope to show that it's right, in the case of an astronomy theory, it's pretty hard to believe. So Einstein's theory of gravity gave us a unique picture of the Earth because it told us that space wasn't this static thing that we normally think of. Now, Einstein got into trouble because in 1916, when he came up with his theory of general relativity, he realized when he applied it to cosmology, to the universe as a whole, that space should be expanding or contracting, should be in motion. And immediately he looked around, and the astronomers of the day told him that the universe was pretty close to static. And so he tweaked his equations. He added something to them, which we'll talk about later, which is a fudge factor that counteracted the effect of gravity and kept them from expanding. In 1929, when it was realized the universe was expanding, he actually had to go back and say, oops, that was a mistake. Well, a big mistake, actually. He always says it was his greatest blunder. So one of the things that Einstein's equations tell us is that the universe is expanding, that means that space itself is being created between galaxies. It's not the idea that the galaxies are moving away from us. So we always talk about the idea of Hubble, of things moving away. It's actually the creation of space, which works almost identically, but there are some subtle differences, which we'll talk a little bit about later on. So if I look at a very far object, the light from that object, which has a wavelength, goes through expanding space, and the light gets stretched as space expands. And so the fact that we see objects redshifted, that is, their light shifted to the red, is not because there's so much moving away from us, but because the light is traveling through space that is expanding between us. And that's a subtlety, which means that it's possible for space to expand more quickly than light can travel without violating relativity. All right, so imagine we have a universe expanding. I want to put it in reverse. If I put it in reverse, I naturally come to the Big Bang. So we expand it, and then I'm going to put it into reverse. As you put things in reverse, things get closer and closer, and eventually they're on top of each other. So it's kind of natural, if you have an expanding universe, for there to be something like the Big Bang where everything is on top of itself. It's quite amazing to me that it took us till really 1966 or 65 to come to grips with it. That was sort of a consequence of the expanding universe. It had been brought up a couple times before, but more or less ignored until the discovery of the cosmic microwave background, that image of the universe just after the Big Bang. So let's look at what this means. Imagine that I have the distance, I have two galaxies. They're separated by some distance, which is at a time right now. So that's that little red dot up there. Now, if the universe is expanding and I want to extrapolate to what happened in the past, I have to draw a line because those objects are getting closer and closer over time, and there's this trajectory. Where that trajectory is such that those galaxies are right on top of each other, well, that's the Big Bang. So how fast the universe is expanding, which is telling you how fast those galaxies are moving apart in the future or getting closer in the past, tells you how old the universe is. So it's a very important thing that Hubble measured. Now, when Hubble measured the age of the universe by this method, he got an answer that the universe was about 2 billion years old. But we already knew back then that the Earth was at least 4 billion years old. And so astronomers, well, we're not that fussy, but we generally speaking like the things in the universe to be younger than the universe is. If it's not, you sort of think maybe we got a little problem. Well, it turns out measuring distances in the universe has been very difficult. It turned out to be what I did for my PhD thesis. And we call the rate that the universe expands the Hubble constant. And so astronomers have funny units. Turns out our units are called kilometers per second per megaparsec. But I'm really going to use the units of age. And so for my thesis, I measured that the Hubble constant had a value of 73, which is about 14 billion years in age. And I'm proud to say that in subsequent time, I think maybe I got a little lucky in my thesis, that we decided that the Hubble constant now is about 71 or 72, depending on who you talk to. And the person, there was a group using the Hubble Space Telescope to make this measurement, and they just received the Gruber Prize, which is a prize I received a couple years ago for this measurement. And one of those people is a Canadian, Wendy Friedman. The other person was my former boss, who was the director of Mount Stromlo, Jeremy Mould, and there was a Minnesotan, Rob Kennicott, and I have family from Minnesota, so I feel as though I sort of have connections all around here, so it was great. So the Hubble constant's about 14 billion years old, but I haven't told you all the story. How fast the universe is expanding tells us how old the universe is, but you can expect the gravity of the universe to pull on the universe and slow it down. And indeed, Einstein's equations tell you this will happen. There's nothing for free, and if there's a bunch of gravity in the universe, as the universe expands, essentially the gravity of everything in the universe collectively pulls on everything else and slows the expansion down over time. So my diagram I showed you is a little different. Imagine I have my universe, and there's nothing in it. Now, we know there's nothing in the universe because we're all here. But if it was only us in the universe, that's effectively nothing because that means there's not much. So if the universe doesn't have much gravity, it won't slow down. It just coasts. It runs that trajectory. On the other hand, if the universe has a lot of stuff in it, then it takes a different trajectory. In the past, it was expanding faster, and then it slowed down. So it has this funny trajectory such that you can see the Big Bang was not as long in the past as we expected. So it turns out that if you take a theorist-type model for the universe, that the universe could be as young, with my value for my thesis of the Hubble constant, of about 9.5 billion years old. Now, people like Bill Harris here have gone out and done their best to measure how old stars are in the universe, and he's pretty confident it's more than 12 billion years old. So there was always a problem during my thesis of understanding why the stars are 12 billion years old, and my value of the Hubble constant was 70 or 14 billion years old, which converts, if the universe is slowing down very quickly, to about 9.5 billion years old. The easy solution was that the universe isn't slowing down much, but the measurements of the Hubble constant were sufficiently difficult that we had to move on. So the other thing we have to think about is the future consequences. It's one thing to look back in time, which we can do quite well, because we can actually imagine looking back in time by looking a long ways away, but we always want to see into the future. So let's look at the consequences looking into the future. So we have our normal universe, which isn't slowing down at all. There's not much in it, it just keeps getting bigger and bigger without slowing down. That universe is infinite. It keeps going bigger and bigger and bigger. It goes on forever. Now I'll show you that it's not just infinite in time, it's actually infinite in space, but that'll be a couple slides down. Now imagine that we have a universe which is slowing down. Well, this is a universe, if it has enough gravity, will reach a maximum size, stall, and then start to collapse on itself. So you can see here that we have the Big Bang, and this naturally leads this type of universe to the Gnab-Gib, which is the Big Bang backwards. So I've always liked this idea for a universe. It has a certain finality to it. But unfortunately, the universe is not always into my aesthetics. So it struck me as a good thing to do was to go out and try to measure this. Now, before I go and tell you about how we tried to measure this, let's look at what this all means. So the slowing down or speeding up of the universe affects how old we think the universe is from this Hubble constant or expansion rate. It tells us the ultimate fate of the universe. And it also tells you something that's probably not obvious to you, but this is, again, thanks to Einstein. It tells us the shape and weight of the universe. So what do I mean? Well, here's a three bears story of the universe. We have a heavy universe. A heavy universe is one that has a lot of stuff in it, and the universe has enough gravity to not only halt the expansion in the future, it also tends to make space bend onto itself. So this is a universe which is finite in space as well. It's a universe which, if I have a lot of time and I head off this direction, I will eventually come back to where I stand. Now you say, how does that work? What am I curving into? The answer is we're curving into that very nasty fourth dimension. Now, the fourth dimension is something that Einstein's theory is all about. And testing Einstein's theory shows when the light bends around the sun, that Einstein's version of this fourth dimension really does exist. At least he's predicted what would happen, and he got it right without knowing it was going to happen. However, I would be lying to you if I said I had a great intuition of this fourth dimension. I have met people who say they really understand the fourth dimension well. My experience is they're people I try not to eat dinner with or anything. It's a very tricky concept, and these people have a certain way of looking at the universe which is, I guess, different than people like myself can do. So I think you just have to accept the fact at some level that we can test whether or not this dimension is there, and then we go through and we use mathematics as an astronomer to understand exactly what's happening. On the other hand, we could have a light universe. So a light universe is one that doesn't have much stuff in it, and naturally space bends away from itself, again according to Einstein's theory. And finally, we have the just right universe. I should say the light universe is infinite, it goes on forever. The just right universe, well, it's just right. It has just the right amount of stuff, right amount of gravity, that space neither bends onto itself or bends away from itself. It's also just right because theorists who try to understand the earliest times right after the Big Bang have come up with a model to sort of explain how the universe is like it is, and they predict that the universe should be just right. Okay? So, imagine we want to do an experiment where we're going to try to understand what the universe has done over time. We're going to look into the universe's past. Now, I told you for my thesis, I measured the expansion rate of the universe now. And so, imagine that I could look into the past. Well, how do I look into the past? I look at very distant objects, and I can measure how fast those objects are moving away from us and how far away they are. And if I look back 10 billion years in the past, I'm actually measuring what the universe was doing 10 billion years ago, not now. So imagine a universe which is empty. It's coasting. It's not speeding up. It's not slowing down. So if I do my little experiment here, I'm going to get a line which is straight, that the universe isn't changing its speed over time. On the other hand, if I have a universe which is slowing down and is eventually going to collapse, it'll follow a trajectory such as the yellow one there, or one that's sort of on the bottom side of the diagram. If the universe is on the other side of that trajectory, then gravity loses, and although it maybe slows down a little bit, space keeps on getting bigger and bigger forever. So that trajectory, that yellow trajectory, is sort of the place where things are right on the knife edge. They're just right, where space has just the right amount of material, not bend onto itself and be finite, and not quite be infinite. It's right on that knife edge where you can't really tell. Finally, you could imagine a universe that was speeding up. So this is a universe that, if we look in the past, will be slower in the past and faster now. That would be indicating something other than gravity as we understand it is at action in the universe. And that, of course, would be a very interesting thing indeed. So how are we going to measure this? Well, we need a standard light bulb. Now, a 100-watt light bulb is not going to do us. But we do have something that is intriguingly good called a Type 1a supernova. So here's a picture of a Type 1a supernova taken with the Hubble Space Telescope. But to understand what these things are, let's look at the history of, for example, our own sun. So our sun lasts about 10 billion years. It's 5 billion years through its life. But in 5 billion years, it's going to get very big and probably swallow the Earth, or not, maybe it'll come close to that. And eventually, its center will collapse down to a tiny little star called a white dwarf star. A white dwarf star is about the same mass of the sun, so about 1 million times the mass of the Earth, but it is the mass of the Earth. So that means that instead of a teaspoon of Earth weighing 10 grams, it's going to weigh 10 tons. And so these are amazingly funny little stars. And that's what our sun will eventually turn out, and that star will just sort of fade away into oblivion. Imagine instead we had not one sun, but our sun had a friend, a binary star. Well, the first star goes and does its thing, just like the sun would. And the star that's just a little smaller will do that a bit later. But this time, the material, and stars don't get destroyed by other stars usually, this material will get siphoned on to the other white dwarf, and that white dwarf, under certain circumstances, can get bigger and bigger and bigger. This is interesting because Chandrasekhar, one of the great astronomers and physicists of the 20th century, showed that when a white dwarf star becomes 1.38 times the mass of our sun, it becomes a giant thermonuclear bomb. And so you end up with a supernova. Now, these supernovae are amazing events. They're 5 billion times brighter than our sun. A little tiny thing, smaller than the Earth, becomes 5 billion times brighter than our sun. They expand at 10% of the speed of light, and they produce most of the iron in our bodies, on Earth, etc. So they're quite important objects, but they're also a standard light bulb. But instead of being 100 watts, these objects are a 1 with 43 zeros behind it, watts bright. So they are a great thing, and it turns out they're useful to about 7% in accuracy. Now, I was telling you astronomers are happy with factors of 10. Suddenly we have something that's good to 7%. Now, 7% is better than any light bulb you would buy at the store is, in terms of when they say it's 100 watts, they don't mean it's 100 watts. They mean it's about 100 watts. Well, these things are about 1 with 43 zeros behind it. but they're within 7% of that number. So we have this great thing we can go out and measure. All right, so the problem with these objects, well, they actually take about 20 days to rise and fall and fade into oblivion. And the problem with these objects, they're very rare. So an object that was seen from Earth was seen in 1006 AD, seen by the Chinese, also seen in Switzerland at a monastery. And this object was insanely bright. It was as bright as the half moon, but it would have been a little point of light. And little points of light, we're just not used to seeing that bright. You would have created little reflections in our eyes, would have been visible during the day. And that object is one of 3 such explosions in our Milky Way in the last millennium. Excuse me. So they don't happen often. Just to show you what one of these objects looks like now, not in the optical, but in the X-ray, there are these big ball, and if we look at that carefully, we see it's full of iron and all the interesting things that these things produce. So the key is being able to find these things, because they only happen once every 300 or 400 years in a galaxy. But these have been sort of the prodigal son of cosmology for a long, long time. And in 1993, I had finished my PhD. I was sort of wandering around trying to figure out what to do. And in 1994, it became very obvious to me that doing this little experiment was not only interesting, it was possible. And it was because technology of both telescopes and mainly detectors, that is the things we take pictures of the sky, we had moved on beyond photographic plates, we could go through and do this experiment. I was not the only one with this idea. And so it turned out that 2 teams were formed, which were trying to suck up all the telescope time, as the astronomers in the room will tell you. And it was quite big teams. One was led by myself, and one was led by someone named Saul Perlmutter. Now, we were known here. Saul's the short guy. Saul and my team were renowned for bickering in public. Fortunately, most of these bickering occurred in the United States, and I had by this time moved to Australia, so I only read about it in the email and was, I guess, slightly amused and slightly horrified. But anyway, we're sort of all friends now, at least in public. So what was the idea? Well, the idea was to go through, get lots of telescope time. So this is the CTIO 4 meter. And you can see the sky going by, and we would get this telescope time. We would sip our Chardonnay, collecting photons. What were we trying to do? Well, we were actually collecting a lot of photons and a lot of data. And so we would be taking images such as this one. So this is 1/8 of one image that we would take every couple minutes. In 1995, we were collecting roughly 50 gigabytes of data a night. Now, to the modern generation, you know, you say, well, okay, it's a little more than a Blu-ray disc, but it's not that much. Well, you know, in 1995, we did not have Blu-ray discs. We had 2 gigabyte hard drives. And so this required us lining up 25, computers and hooking them all together as best we could and attempting to write software, which was my job, to sift through this stuff and find the supernova. So here's the challenge. 5,000 galaxies in this image. Find the supernova. Well, okay, it's a little difficult. I'll point it out to you. It's right there. So it's the little dot on the side of the galaxy right in the middle. And how do we know that? Well, I've cheated. We don't just take one image. We actually take 2 images. So here is an image taken on the 28th of April. And here is an image taken 24 days earlier. And you can see that nothing has become something. That little dot on the side, that supernova, was 5 billion light years in distance. It exploded before the Earth was formed. And that's the power of cosmology. I always love to think that we can travel in time. Unfortunately, we only get to go one way, which is back in time when we look. And we move very slowly forward in time ourselves. So there's no way to look forward in the time, really. We only have to guess the future. But we really can, as astronomers, look and see the past, as long as we're willing to look a long ways away. All right, so we found this one, and we found several other, not lots, because it was hard work. And in 1998, we plotted our data up in the experiment that I showed you we were going to do, and we got a diagram that looked like this. So we have faster expansion on the bottom, slower expansion at the top. The line in the middle is showing you a line which nothing happens. Now, and we're able to find objects as far back as about 8 billion years into the past. So I'm going to put in the trajectory of the side of the diagram where gravity wins. This is where the universe is finite. So the nearby objects, the ones that are relatively near in time, each object is represented by a line which tells you the uncertainty of that object. So in terms of an astronomer's view, that line tells you where 2 out of 3 times the object will be in that little band. 1/3 it can be outside, but usually not too far. So the nearby objects, on average, sort of lie anywhere in the diagram. But the distant objects, you can see not a single one lies in the trajectory where the universe is finite, where the universe is going to end sometime in the future. More interestingly at the time was that the yellow part of the diagram shows you where the universe is slowing down from gravity. And you'll notice that a few of the objects are consistent with that, but on average, all of the points lie in this unexpected part of the diagram, the place where the universe is not slowing down, it's speeding up. Now, you might think that I would have gone whoopee when I saw this. I actually got this sinking feeling in my stomach in the end of 1997, thinking, I have spent 3 years of my life to make a giant mistake. What am I going to do? Well, the answer is we checked our work very, very carefully before we became convinced. Eventually, we published a paper. It turns out that we weren't the only ones to publish a paper. Our friends, Saul Perlmutter's group, at the same time, without us knowing this, were getting the same crazy answer that we were. Now, these two groups were well known for not agreeing on anything in public. And so the fact that we finally both came out independently, simultaneously more or less, with the same answer, maybe provided a false sense of security to the community that somehow we got this right. Anyway, just to show you that this is not just my work, it was a huge number of people, 20 people on our side, over 30 people on Saul's side, and most of these people really did spend most of several years working on this work collectively, so it was a pretty big enterprise. So people often ask, did we have a eureka moment? Did we have that moment when we thought we had it? So Adam Rees was a young postdoc. He was actually the only person on the team younger than me, so we decided in our team to shake things up and have the young people who are doing the work actually run the thing. So that was, I think, a good thing that no one actually, after the fact, thinks it was a bad idea, although at the time there was some worries about the concept of having 28-year-olds run a project of 30 people. But Adam was the person in charge of looking at this data, and this shows his lab book, his real lab book, the first time he went through and tried to calculate with his new data he had been working on what the universe was doing. And so he was measuring how much mass there would be in the universe, so that's telling you the fraction of the amount of material necessary to make the universe just right, to make it the universe, that place, that knife edge between being open, being finite, and infinite. And the number he got was the amount of material in the universe was minus 36% of the amount. Now, I don't know about you, but to me, mass is always a number which is positive. That is, there aren't negative U's, at least I don't think so. And so when we got this number that there was a negative amount of mass in the universe, that sort of indicated that there was a problem in the basic understanding of what we were going for. Now, I don't really know what Adam thought, but I do remember Adam, the day that he did this in his lab book, calling me up in Australia at 3 in the morning, which Adam always managed to get confused on the time zone difference. My wife said expletives, and he told me about this, and I said, oh, Adam, what have you done now? You know, essentially, I said, I'll worry about it in the morning. So anyway, for 6 weeks, we toiled away and remeasured everything, and so there was no eureka moment. It was a sort of a gradual realization that at some point, we were going to have to front up to the rest of the community and tell them the universe is speeding up for reasons unknown. And that was something that was fairly terrifying. It turned out that it was something that the community was surprisingly accepting. But in the end, our final analysis said the universe is accelerating. And when you go through and try to figure out how it would be accelerating, you sort of realize that you have to have a 30% of the universe be stuff that has gravity, like atoms or other things, and 70% of the universe has to be something else that does the other thing. It pushes on the universe. And so we needed this very funny mix, and we call that 70% matter, this mystery matter, we call dark energy. But of course you had to believe our results. So this did catch a bit of attention in 1998, and so people worked very hard. And one of the things that was done was this map of the sky, where they sort of did a census of gravity by looking at hundreds of thousands of galaxies, and that allowed them to weigh the universe, to measure how much gravity there was in the universe. And so this program done in Australia and a similar one done in the US a couple years later both came to almost exactly the same answer, which is that when you weigh the universe, it has 27% of the amount of stuff that has gravity compared to that knife edge, to that flat version of the universe, that place where the universe is just right. Now you might be thinking 27%, now what's this, how's that compared to what you're saying? Well, these guys cannot see dark energy. They cannot see stuff that pushes on the universe. They can only see stuff that that has gravity in the normal sense. The other thing that happened was this very good measurement of the cosmic microwave background. Now it turns out these little bumps represent 10,000 galaxies, are a place where the universe has begun to collapse. But they have a very special size due to physics. So as a part of the universe starts to collapse and get smaller, it heats up and creates pressure. And the pressure eventually has the same ability. It can push on the universe as much as gravity attracts it. And that pressure doesn't work at the speed of light. It actually works at the speed of sound. Now, the universe, when it was very young, is very, very simple. It turns out that the speed of sound in this universe can be calculated to insanely good accuracy, probably 15 decimal places, because it is the speed of light divided by the square root of 3. And my calculator has 15 decimal places, so I'm pretty comfortable with square root of 3 after that far. So we have a scale in the universe which the bumps in the universe where pressure stops the expansion are going to have a size of the speed of sound, so 57% of the speed of light, times the age of the universe. And the age of the universe in this picture is 380,000 years. So we have a cosmic ruler. Now I told you earlier on we didn't have cosmic rulers. Well, until 5 years ago we didn't have a cosmic ruler. But when these measurements were made, we suddenly had a cosmic ruler. We knew exactly how big these bumps were in the universe. Unfortunately, this ruler is not nearby. It's way back. It's this back when the universe was only 380,000 years old. Turns out that we can use that ruler to measure the geometry of space. Now, this is a very somewhat sophisticated argument, and so if I lose you on this, it's okay. The next slide we'll get back to stuff. So physics is telling us how big these blobs are in meters. Now if I take a ruler and I put it up close to you, as I move away, the ruler becomes smaller and smaller. So I can use this ruler and how big it appears, what its angular size is, to gauge the distance. And it turns out that when we measure how big those blobs are, they're roughly a degree across. And it turns out that how big they appear tells us the shape of space. So let me show you a diagram. I have a blue curved space. So this is a finite, a version of space which is finite. And then I have the red line is a universe which is on that knife edge, which we call flat. The red line and the little blue lines in the center, when viewed from the Earth, look the same. Those things are going to have the same size. So this blob and this blob, the big blobs and the little blobs here, the big blob in the flat space appears exactly the same size as the small blobs in the curved space. So objects of a similar size appear larger in a finite curved space. So by looking at how big those blobs are, we can see, is the universe flat or is it curved? So if I lost you there, let me show you in a more systematic, schematic way. here is our model of those blobs and what it would appear in the open, that is the universe that's infinite, the universe that's on the knife edge in the center, and the universe which is finite on the other edge. As you can see, in the finite universe, the blobs are big. In the universe which goes on forever, they're small. And the knife edge, they have a certain specific size. Well, when we look at that data, it looks exactly like the flat universe. In detail, the universe seems to be within 2%, and that's as accurately as we can measure it, of being on that knife edge. Now, you might be wondering now, how does that compare with that number of 27%? Well, it turns out the geometry of space that is sensitive, the stuff that warps space, is not just gravitating matter. It's any type of matter. Any type of matter, including dark energy type matter, will warp space. And so that allows us to do some cosmic subtraction here. The cosmic microwave background tells us that the universe has 102%, plus or minus 2%, of the amount of material necessary to be on that knife edge. The census of the nearby universe tells us that 27% of that has gravity, leaving us 75% of some form of mystery matter, which seems exactly the same stuff that the supernovae have seen. So we have consistency. When we look at and put it all together, everything we know, this messy version of the universe seems to describe everything we know, which is that 4% of the universe are the atoms which you and I are made up of. Another talk that could be equally long to this one shows that of the 28% of the universe that has gravity, 24% of it is what we call dark matter. And we don't really know what dark matter is yet. More on it later. But even more embarrassingly, 72% of the universe is this dark energy, this stuff that seems to be pushing on the universe that we have very little idea what it is. So what might this dark energy be? Well, we're going to go back and look at Einstein. As you recall, Einstein, when he invented the equations of general relativity, realized that there was a problem because they made the universe expand or collapse onto itself. And so he invented an energy tied to space itself. And that energy, turns out, pushes on the universe and causes it to speed up over time if it exists. Now, of course, he later retracted that idea that the universe had this thing in it and called it his greatest blunder. But the beautiful thing about Einstein is Einstein's greatest blunder is certainly my greatest achievement. And that's the type of guy that Einstein was. So it's this energy that is tied to space itself. As you create space, as the universe expands, you get more and more of this stuff over time. This sets up, turns out, a battle of dark energy versus gravitating matter, which I'm going to call dark matter because it looks good on the slide. So dark matter. What is dark matter? Well, I encourage you to go to a talk on dark matter at some time. But we are, I won't say relatively positive, I would say that we have a good guess that it could be some undiscovered particle, for example, similar but much bigger than the neutrino. And neutrinos, turn out, can pass right through the Earth, so they're very hard to detect. We often call those things WIMPs, weakly interacting massive particles. As the universe expands, the amount of dark matter stays the same, so its density and its gravitational effect gets smaller over time. So the more space expands, the less ability dark matter has to influence the universe. On the other hand, dark energy is tied to space itself. As the universe expands, the dark energy gets created with space, and so it becomes stronger and stronger relative to dark matter over time. So we have this interesting situation where we can sort of, let's see. The problem, it looks a little different here. So here's a little schematic diagram of the universe. The universe starts out expanding. There should be a lot of dark matter slowing things down, and it's only when space gets to a certain size that dark energy can start to rip the universe apart. So this makes a prediction that if we look into the universe's past, the universe should not always be speeding up. It should be slowing down if we go back far enough and speeding up later. So how far back can we go? Well, it turns out the Hubble Space Telescope is an amazing thing. This is how far back we can look back. This is the most distant exploding star ever discovered, a supernova that happened 11 billion years, or only 2 billion years after the Big Bang. I can't really show you anything else about this object except for to tell you that when you go through and measure the expansion rate of the universe back then, it indeed was slowing down back then and has only started speeding up in the last 7 or 8 billion years. So what's consistent was the prediction. We went out, we tested it, and we got the answer that was predicted. So what's the goal of the future? Well, we really want to understand dark energy because we do not have a clue. Our best guess is Einstein's version of the cosmological constant, that is energy tied to space, but we don't have a good motivation why it would necessarily be there. So the big question we have is, does it get created exactly with space, which is what Einstein's version would? So as space doubles in size, for example, does the dark energy double exactly in size? Or does it do that a little bit faster or a little bit slower than that Einstein prediction? And this turns out to be one of the biggest physics questions in Canada, which has done a lot of work in this, the US, Europe, Japan, and Australia. So imagine that we have a universe where Einstein's version of it is right. Dark energy is tied to space itself. Well, in this case, dark energy gets created exactly as space gets created, and dark energy has already won the battle of the universe. The universe is getting bigger and bigger over time, so dark energy is getting more and more prevalent compared to the matter that has gravitation. And so this dark energy will continue to accelerate the cosmos. Now people often say, well, does that mean I'm expanding and I'm going to get ripped apart? No. It turns out that our part of the universe is not expanding. This auditorium is not expanding. Your body is not expanding. The gravity and the nuclear forces in your body, the chemical forces in your body, have stopped the expansion of space a long time ago. So dark energy has not been able to get in and rip you apart. And so you are always safe. Unfortunately, from a cosmology point of view, the rest of space will continue to expand faster and faster, and the creation of space between us and other galaxies are going to happen faster and faster, even to the point where light will not be able to get to us from nearby galaxies in the future. And so from a cosmology point of view, we have a real tough time in the future because there's not going to be anything to look at. We're going to be in our own super galaxy. It turns out the Andromeda galaxy is falling towards us. So our part of space, gravity is one. Dark energy is not taking over that little tiny piece of space. But there's only a few galaxies that are really in our little bubble. We're all going to merge eventually and form some big blob. And we're going to look out into emptiness. Now imagine we have something a little more exciting. Imagine that dark energy gets created a little faster than the creation of space. Then it turns out that places that gravity has collapsed the universe are no longer safe. This type of energy can eat away at those previously one parts of the universe, and it turns out they can eat away all the way down to the subatomic level. And so this is a very exciting end of the universe, because the end of this universe, about 15 minutes before the universe ends, the stars above us suddenly are pulled away at faster than the speed of light, and you can't see them anymore. They just disappear. 15 minutes later, you get ripped apart at the atomic level. And that's sort of the end of the universe, where every atom and every piece of every atom is ripped apart to a distance where no light can get between them. So that's certainly, to my view, a version of nothing, at least a very exciting version of nothing. I should say that that doesn't going to probably happen if it happens at all. That's a very speculative theory. But if it does happen, it's probably at least 100 billion years into the future. So we're probably not going to have to worry about it, at least in my lifetime. So I'll just end on the note that it appears that I've tried to give you an idea of how the universe ends. It doesn't appear to end in a gnab, but a whimper, or just possibly in a scream during the Big Rip. Thank you very much.